Hi there, this is Professor Barber. In this lesson titled Trigonometric Graphs, we will learn the periodic nature of sinusoidal curves and how to graph transformations of these functions by finding the transformed period, the amplitude, and horizontal shift. So, the learning objectives of this lesson are 1. Be able to graph the sine function. 2. Be able to graph the cosine function. 3. Be able to find the period, amplitude, and horizontal shifts of the sine and cosine functions. And 4. Be able to graph transformations of the sine and cosine functions. Roman numeral 1. Graphs of sine and cosine functions. The terminal point P, x, y, determined by the number t, is the same as determined by t plus 2 pi. Thus, the sine of t plus 2 pi equals sine of t for any integer n, and the cosine of t plus 2 pi equals cosine of t for any integer n. Thus, the sine and cosine functions are periodic. We define the period of a periodic function f to be the least number p such that f of t plus p equals f of t for every t. If f has a period p, then the graph of f on any interval of length p is called one complete period of f. Using this definition, we establish that both sine and cosine have period 2 pi. Graph the basic sine curve between 0 and 2 pi. I begin this by marking on the unit circle the 4 axis points with their t values. For example, at t equals 0, so we'll do t equals 0. It corresponds to the ordered pair 1, 0. The unit circle trig function states that for the ordered pair xy on the unit circle, the cosine of t corresponds to the x, and the sine of t corresponds to the y value. With that, the sine of 0 is 0. At t equals pi over 2, that's a quarter of the way around the circle, the point on the unit circle is 0, 1. The y value of the ordered pair is 1. What that means is that the sine of pi over 2 is 1. Continuing around the circle, we'll get to t equals pi. The corresponding ordered pair is -1, 0. So the sine of pi, which corresponds to the y value, is 0. And at, let's keep going, t equals 3 pi over 2, the ordered pair is 0, -1. And the sine of 3 pi over 2 is the corresponding y value, which is -1. And concluding the 1 revolution, that's at t equals 0, which is the same value as t equals 2 pi, that's 1 period. The point is 1, 0, and sine t is the same as was for t equals 0, which is 0. Now let's complete the table. The table presented has 2 columns and 5 rows. The first row labels the columns t and sine of t. I've used values marked on the unit circle to complete the table. The arrow notation here means from and to, as in from 0 to the value pi over 2. Let's look at the row below the labels. As we traverse from 0 to pi over 2, knowing that 1, the function is smooth and continuous, and 2, we know the sine values at the axial t's. As t traverses on the unit circle from 0 to pi over 2, sine t begins at 0 and goes to 1. As you travel from pi over 2 to pi on the unit circle, the sine value goes from 1 to 0. As we continue traversing from pi to 3 pi over 2, the sine value goes from 0 to -1, and as we traverse from 3 pi over 2 to 2 pi, sine at 3 pi over 2 is -1, and at pi the value is 0, so it traverses from -1 to 0. Let's mark these points on the actual XY grid. The points we are plotting, the T's are along the x-axis or the horizontal axis, and the sine value, f of t, is the y. So at 0, the ordered pair, or the corresponding sine value is 0. At pi over 2, the corresponding sine value is, we'll call this 1. At pi, sine is 0. At 3 pi over 2, the sine value is -1, and at 2 pi, when t is 2 pi, sine of 2 pi is 0. For some more guidance, let's evaluate the sine at some points between 0 and pi over 2. I like to get values of the sine for pi over 6, pi over 4, and pi over 3. At t equals pi over 6, the ordered pair on the unit circle is square root of 3 over 2, 1 over 2. We want the 1 over 2, which is the sine value. So we plot pi over 6, 1/2. The sine of pi over 6 is 1/2. Let's look for the sine of pi over 4. At t equals pi over 4, the point on the unit circle is square root of 2 over square root of 2. And so if we're looking at this for the sine, we want the y value. So when t equals pi over 4, the sine of pi over 4 is the square root of 2 over the square root of 2. And then finally, let's go to pi over 3. At pi over 3, or the distance of pi over 3, the point on the unit circle is 1/2 square root of 3 over 2. We want the corresponding y value for the sine. So the ordered pair that we will have is pi over 3, and the sine of pi over 3 is the square root of 3 over 2. Let's plot these points. We're going to have to eyeball some of it. Pi over 6 is about 1/3 of the way between 0 and pi over 2, and it's to 1/2. Pi over 4, it's midway between 0 and pi over 2 on the horizontal axis. Square root of 2 over 2 is about 0.7. Then finally, pi over 3, still less than pi over 2, square root of 3 over 2, we plot that point. And now we kind of have a pretty good shape, so we'll plot the points, knowing that this is periodic. The pattern will repeat. And so here we have the graph of y equals sine of t. That is one complete period. Graph the basic cosine curve between 0 and 2 pi. Let's begin with the unit circle, and notice that I've got 4 points marked on the unit circle. They are 1, 0, 0, 1, -1, 0, and 0, -1. Each of these correspond with a specific t value. The starting point is t equals 0. And as you traverse along the circle, quarter of the way, that is t equals pi over 2. Now, the circle trig definition tells us that for every ordered pair xy on the unit circle, x corresponds to cosine of t and y corresponds to sine of t. Since we are graphing the cosine curve, we are concerned with only the x values. So let's notice that as t goes from 0 to pi over 2, the x value goes from 1 to 0. So we'll write 1 to 0. Keep traversing, so we go from pi over 2 to halfway around the circle. That would be t equals pi. The x value, which corresponds to the cosine for pi over 2, is 0. The cosine of pi, so we'll start at 0 for pi over 2, and the cosine of pi is -1. Let's continue. Traverse around the circle, and when we have traveled t equals 3 pi over 2 units of measurement, the corresponding ordered pair on the unit circle is 0, -1. 0 corresponds to the cosine, so we go from -1 to 0, and then we make it the whole period. That's one revolution. So as we go from 3 pi over 2 to 2 pi, t equals 2 pi, which, by the way, is the same value as t equals 0, okay? Then the cosine value goes from 0 to 1. Now we'll use these values to get a sketch of the cosine. Let's remember, the horizontal axis corresponds to t, the vertical axis corresponds to f of t, which is the cosine of t. Let's plot some points. At 0, 2 little dashes up, I'll call it 1, just so that we have more space. Okay? So the first ordered pair is 0, 1. At pi over 2, the corresponding ordered pair is pi over 2, 0. And then at pi, the corresponding function value is -1, so pi -1. At 3 pi over 2, the corresponding function value is 0. And at 2 pi, the corresponding function value is 1. Then we'll connect these points, attempting to keep a sinusoidal or a wave. And so that is one period of the graph of the cosine function. Roman numeral 2, graphs of transformations of sine and cosine functions. Part A, amplitude, for the functions y equals a times sine x and y equals a times cosine x. The number absolute value of a is called the amplitude, and it is the largest value these functions attain. Graph the sinusoidal curve y equals 3 times the cosine of x minus 2. To sketch this curve, we begin with the basic y equals cosine x curve, which we know by heart, and then apply the transformations. The amplitude, looking at y equals a cosine of x, is the absolute value of a, and so we see here that the amplitude here is 3. The minus 2 is outside of the function, so we go back to what we remember about doing vertical shifts and know that we shift down 2 units. We have several options in obtaining the transformation. The easiest or the most straightforward is to retain the shape and relocate it. So the minus 2 tells us the graph is going to be shifted down 2 units from, let's say, the x-axis. The amplitude of 3 tells us that instead of having a height of 1, it's going to have a height of 3 from the new baseline. So I would begin by plotting 1, 2, up 3. This is the amplitude of 3. And then let's go with the basic shape that we do know. We know that at pi over 2, the cosine is 0. And so with the shift, at -2 is where the pi of 2 is going to have the 0 effect. And then at pi, from what would be the baseline, we go down 3, 1, 2, 3. Continue with the behavior at 3 pi over 2. The minus 2, axis y equals minus 2, does the shift. And then at 2 pi, which would be the equivalent of 1, we go up 3 spaces. 1, 2, 3. Now let's attempt to sketch the graph. And we have a graph that is the cosine function with amplitude 3 shifted down 2 units. Roman numeral 2, graphs of transformations of sine and cosine functions, part B, period. The sine and cosine curves y equals a times the sine of kx and y equals a times the cosine of kx, where k is strictly positive, have amplitude absolute value of a and period 2 pi over k. An appropriate interval on which to graph one complete period is bracket 0, comma 2 pi over k bracket. The value of k has the effect of shrinking the graph horizontally if k is greater than 1, and the effect of stretching the graph horizontally if k is less than 1. Graph the sinusoidal curve y equals the negative of the sine of 1/2 x. We begin with the base curve of y equals sine x and then make the necessary transformations. One period of the basic sine curve can be sketched between 0 and 2 pi. We'll begin at 0, 0, increase to 1 as we move from 0 to pi over 2, decrease to 0 as we move from pi over 2 to pi, continue to decrease to -1 as we move from pi to 3 pi over 2, and then increase back up to 0 as you move from 3 pi over 2 to 2 pi. That's one period of the sine curve. Now, let's look at what we've got. The negative in front of the sine tells us that it is reflected or flipped over, however you want. Reflect about the horizontal axis, the x-axis, okay? And the other thing we have to work with is the 1/2 x. The period is determined by 2 pi over k, and so we'll have 2 pi divided by 1/2. That is actually 4 pi. And a standard interval on which this would work, we can graph from 0 to 4 pi. So now we'll take the standard sine curve, flip it, and then change the period from 2 pi to 4 pi. So let's mark 4 pi, 2 pi, halfway between would be pi, and between 2 pi and 4 pi is 3 pi. Let's label the vertical axis, so I'll label this one -1 and label 1. So let's sketch some points. We start at 0, 0 and decrease, because remember we're flipping it about the horizontal axis. Then we go back up to 2 pi. And then we continue to increase to 3 pi and then decrease. I'm going to go ahead and draw arrows to indicate that this goes on indefinitely. I'm just drawing one period. Note that when it's 1/2 x, you need twice the amount of the regular period to get the entire graph in. Roman numeral 2, graphs of transformations of sine and cosine functions, part C, phase shift. The sine and cosine curves given by y equals a times the sine of k times the quantity x minus b and y equals a times the cosine of k times the quantity x minus b for k strictly positive have amplitude absolute value of a, period, 2 pi over k, and horizontal or phase shift b. An appropriate interval on which to graph one complete period is bracket b, comma, b plus the quantity 2 pi over k, bracket. Consider the sinusoidal curve y equals 3 cosine of the quantity 2x plus pi over 2. Part A, find the amplitude, period, and phase shift. Let's do a little bit of algebra so that we can rewrite this in the form y equals a, the cosine of k times x minus b. Okay, so amplitude is the constant that's multiplied to the trig function. We denote it with absolute value of a, and in this instance the amplitude is 3. We increase or affect the height by 3. Now we're going to have to rewrite this expression a little bit to do the period and phase shift. So I'll have y equals 3 times the cosine of, then factor out the 2 from the argument. So I'll have 2 times, factor out means divide, 2x divided by 2 is x, and then plus pi over 2 divided by 2 is actually pi over 4. And let's do one more thing. The standard form has x minus b, so we'll write this as y equals 3 times the cosine of 2, x minus negative pi over 4. Now let's get the phase shift and the period. We've already got the amplitude. Now working on the phase shift. That's the horizontal shift, by the way. And by the setup, we know that the phase shift is minus pi over 4. So if you were looking at a cosine curve, just shift it back, pi over 4 units. Now we need to determine the period. And we can find the period as 2 pi over k. So we're going to have 2 pi divided by the number we factored out was 2. So we get that the period is just pi. Now, let's just write what would be a good interval. So an acceptable interval, okay, is where 0 was. We'll begin with minus pi over 4. And then from minus pi over 4, we need to move over an entire period. And for this cosine function, that period is pi. So we would graph this from minus pi over 4 to 3 pi over 4, and we will get one entire period of this transformed cosine function. Part B, graph the function. We have all of the information we need. First, we need to know the basic shape of the cosine graph, and that we do know. We've got the phase shift. So instead of doing that first period starting at 0, let's start it at minus pi over 4, at minus pi over 4. And it goes over pi units, so we need to get an entire period of the cosine in between minus pi over 4 and positive 3 pi over 4. Let's get our key points. So midway between minus pi over 4 and positive 3 pi over 4 would get us to positive pi over 4. Now let's mark the points. We have an amplitude of 3, so at negative pi over 4, cosine is at 3. At 0, the cosine is at 0. At pi over 4, the cosine is way down at minus 3. At pi over 2, the cosine will be at 0. And at 3 pi over 4, we finish the entire period. That would be at 3. So the graph would look something like write the trig function in the form y equals a times sine k of the quantity x minus b for the given graph. The graph that we have is a sine curve. It looks like it's shifted to the right, midway between 0 and pi over 2, so that would be pi over 4. To complete this equation, we need to find the values for the amplitude A. We also need to find the phase shift, and that phase shift will give us the value that's B. And we also need to find the k associated with the period. We need the k on the 2 pi over k. So, looking at this, we see that the height is 2, the lowest point is negative 2, so we get that the amplitude is 2. We've got the value for A. The phase shift, the sine curve starts midway between pi over 2 and 0, So we'll say that that is pi over 4. It's moved to the right side, so we'll say that the phase shift is b equals pi over 4. And now we have to solve for the k. The k is obtained by taking the period of the graph and solving for it equal to 2 pi over k. This graph's period is 2 pi. So we've got 2 pi equals 2 pi over k, and when we solve for this, we get k equals 1. Let's put the values of a equals 2, k equals 1, and b equals pi over 4. And so the correct form would be y equals 2 times the sine of k is 1, so we don't need to write the 1, x minus b, the phase shift, is pi over 4.